Hello, good morning, everyone. My name is Michael. I'm assistant professor in EC department, and I'm glad to be here. Thanks for inviting me. So today I'm going to talk about metamaterial antenna-based multi-target vital sign detection and motion tracking. So this is one of our recent projects. So some background for the motivation of why we're doing this. So usually if you go to like a supermarket and then get a infrared sensor or so-called IR sensor to do the motion sensing for human beings. So usually the off-the-shelf IR sensor cannot provide any information of the location. It can just tell you whether there's a human being or not. So and then not to mention it can measure any vital sign. So recently, people have been starting using this microwave-based radar to detect humans' movement and then also their vital sign signals. And as you can see here, conventional microwave-based radar system for human detection, since the antenna itself is only omnidirectional, so there is no beamforming capability, so they cannot really detect where the human is located. They can only sense the displacement of the human being and then also the presence of the human being. So to do the beamforming and then to be able to detect multi-target, you have to do some sort of beamforming, right? So usually the antenna has to incorporate so-called phase array or for electronic beam steering. Or in addition, you can use mechanical rotor-based beamforming as well. But the problem is that it will, as you can imagine, this will increase the cost, right? Because you want to make sure that the cost cannot be too much so that we can make everyone afford this kind of portable device. And also it will increase the system complexity. So this is why we wanted to use this so-called metamaterials type of electromagnetic structure to design our antenna interface and then try to improve this multi-target sensing scheme. So what is metamaterials in electromagnetic waves? So if you have EM waves or electromagnetic waves that's impinging in a medium that consists of epsilon 1 and mu 1, which is its permeability and permittivity. So in nature, these two quantities, they are by itself, they are larger than zero. They're always going to be positive quantities. But if we properly design the periodic structure of its pattern of the medium itself, we can actually manipulate these properties, which we call constitutive properties of the EM materials. So we can, if we properly design this periodic structure, we can actually make it as a effective permittivity and permeability as we wish to achieve the value of it. So if we carefully decided these two quantities, they don't have to be positive. They can be negative quantities as well. And later on, we will see how this can actually help us to design our antenna structure. So metamaterial in general is a artificial EM materials with novel, which is unconventional, effective medium properties such as permeability and permittivity, which cannot be found in nature. So as we have all known, EM waves are governed by the famous Maxwell's equations, right? So you have electric field and then magnetic field coupled to each other through the Maxwell's equations. So when the wave is propagating inside medium consisted of this epsilon mu permeability and permeability, we can obtain its propagation constant, which is in terms of these parameters. And on the other hand, in microwave community and also for microwave circuits, the most commonly used component is transmission line structure. So if we look at its mathematical interaction between the voltage and current that's describing the wave propagating transmission line, you can see how similar this equation is compared to Maxwell's equation if you just simply map electric field to voltage wave and then magnetic field to current wave. So this is so-called telegrapher's equation in transmission line. So if we can, that means if we can properly design the medium for like a conventional EM medium, if we use the same principle, we can also, if we somehow design our transmission line structure, we can also manipulate the transmission line into a so-called metamaterial transmission line structure just by properly designing this transmission line structure. And we also know that transmission line consists of a unit cell that has a series L and a shunt C. So the problem is that how we can how we can put it in a metamaterial form of transmission line type of structure. So as you can see here, this is a conventional transmission line. We have series L and then shunt C. And if you derive its group velocity and phase velocity, since beta propagation constant is always going to be a positive quantity, so then it will be a linear relationship with the frequency. So in this case, both group velocity and phase velocity, they are positive quantity. But now if you flip L and C, if now you have a series C and then shunt L, and you derive the, I'm just going to omit the mathematical derivation, but if you derive the beta, which is propagation constant, you will see now it's become a pure negative quantity here. So this negative propagation constant, this is actually artificial synthesized. It cannot be found in nature. So in this case, we can call it a either left-handed transmission line structure, because now it's not going to follow the right-hand rule. It's going to follow the left-hand rule. So this is one kind of metamaterial type of transmission line structure that we can synthesize using transmission line. But in reality, actually, these two will, because you will always have inevitable parasitic effect. So in reality, you will always have these four, which is series L and then series C and then shunt L, shunt C, come all in together. So meaning that you will have the conventional property and then the metamaterial property. They are both going to be integrated together. So in this case, we refer this transmission line composite right-left-handed transmission line, because at low frequency, it's going to be governed by the metamaterial property, which will follow the left-hand rule, and then at higher frequency range, you will see the conventional property will start pop out. So it's going to follow the conventional right-hand rule property. So what can we do with this metamaterial-based transmission line? Is that if we, as compared to the traditional transmission line, which is always a linear relationship, and it's always going to be a guided wave structure, meaning it's not going to, we cannot use it as an antenna. It won't radiate anything. But with the metamaterial type of transmission line, there's one interesting property is that because we look at the dispersion curve, which is tells you the propagation constant beta versus frequency relationship, we can see that it will penetrate with so-called radiation regime, which is bounded by these two, we call it light line, that has a slope of speed of light. So within this region, the EM wave can actually radiate, and the main beam of the radiation pattern is indeed depending on the propagation constant beta. And as we mentioned before, because this beta can now be both negative and positive, so that means we are able to scan the main beam, which is the theta here, being a function of frequency. So the main beam can be steered from the backward side to broad side, and then continuously to forward side gradually, just by simply sweeping our center frequency. So in ideal case, a one-dimensional metamaterial-based transmission line, so as you can see here, is a periodic structure. If we use it as an antenna structure and we just simply sweep the frequency, ideally it can be swept from negative 90 degree and then continuously to broadside, which is 0 degree, and then gradually move to the other side, which is plus 90 degree. So this gives us a very simple frequency to space mapping mechanism just by changing the center frequency. So we can, so for proof of concept, we came up with the idea that we can just use this to do a simple target detection, right? So we just, first we place a different target at different location, and we place our metamaterial-based antenna in connection to the source, which in this case we use negative analyzer here. And then for receiving, we use a broadband Hall antenna. So this negative analyzer will just basically give a bunch of, it's a chirp signal, so we'll give, which consists of a bunch of frequency components. In this case, we use it as an X-band, so it can roughly go from 8 to 12 gigahertz. So depending on the frequency, right? Because different frequency will be mapped to different space in this case. So we will see that each angular location will be coded using a specific frequency component. And then by simply detection the spectral component of the reflected wave, then we can readily detect where the target is located in terms of the angular direction, right? Just by mapping the reflection spectrum to the dispersion relationship that we obtain from the antenna. So we also use this to do multi-target detection. So if we put two metallic structure in front of it, and then we can read the reflection spectrum, then by mapping the dispersion relationship, we can readily obtain the angular direction of the target's location. So this can give us a advantage such that this kind of radar sensing scheme can have both very fast sensing speed and also very wide field of view, because theoretically it can go from -90 to +90, which will give you a 180-degree field of view in one dimensional. So we utilize this, we want to move one step further. So we utilize this characteristic, and then we build a radar sensing module, and then to see if we can detect some Doppler signatures, such as human movement and then vital sign detection. So in this case, we built our new liquid antenna, or just metamaterial-based antenna that consists of 10 unit cell here. So as you can see, because it has to follow that series C and then shunt L structure. So as you can see here, the gap will form the series C, and then this, you see some white pad there. There's just a virtual ground to the ground plane, so that will give you shunt L. So by using this, and then we designed the center frequency in around 24 gigahertz band. So if we scan the frequency from 24 to about 27 gigahertz, you'll clearly see that the main beam is changing its direction. So we use this antenna as our transmit and receiving antenna, and then we put it into a, also we made the radar, this module by ourselves using the off-the-shelf components. So we have a radar chip here, which is off-the-shelf component. I think we use Infineon that can sweep from 24 to 27 gigahertz. And then we connect it to a microcontroller unit, and then finally connect to the computer. So by changing the frequency, and then we can basically obtain the information of different targets' location and then their Doppler information. And here shown a prototype of the fabricated 24 gigahertz metamaterial-based liquid antenna. So yeah, this is a prototype here, and then this is the measure result using the turntable, and then neck normalizer in our lab. So yeah, so clearly you can see it again, right? From if we sweep it from 24 to 27, you can see the main beam gradually changes location. So later on, we plan to use this antenna as both transmit and receive, and then in connection to our radar sensor module. And then in this case, because we want to make it portable, so we further integrate it with a Bluetooth module, so everything can be made portable, and then just in connection with the metamaterial-based antenna. And then we would like to do the multi-target sensing in this case. So yeah, so just to briefly explain how this works. So first, the microcontroller unit will just send a command to the radar chip that can sweep from 24 to 27. So it just tells you which center frequency that it's operating right now. So once radar chip receives the command, it will just illuminate the center frequency. So based on the center frequency, it will go to different angular direction based on the metamaterial dispersion relationship. And then the reflected signal will be received by the receiving part, right? And then it will go to the radar chip and then down converted to the baseband. And so the baseband signal will be down converted to an in phase and then quadrature phase signal, or so-called I and Q, and then to the ADC, and then be digitized to the Bluetooth module, and then the Bluetooth module will send the digitized IQ signal to the PC, and then we can do some further signal processing. So this module itself can be made portable, so you can place anywhere. So this is our the schematic of our measurement setup. So we have our 24 gigahertz metamaterial based radar sensor module. So we place in front of two human targets in about 1 to 2 meter distance. So yeah, so by just controlling the radar sensor such that it can sweep from 24 to 27 gigahertz, so the main beam can be kept changing its direction. So yeah, as you can see in this game, 24, so lower frequency part will be shooting to the backward direction, which corresponds to roughly about 24.3 gigahertz. So this will illuminate to the target B in this case. And then the higher frequency part will goes to the forward side. So in this case, we will be illuminating on the other target, which is target A. So just some explanation of how we can do the signal processing in this game. So first, we need to calibrate the DC offset, because the baseband signal that we obtain from the downconverted signal from the MCU actually will contain some DC offset, which is from the static target or some circuit imperfection. Because this these two DC terms, they basically just constant terms, and they will affect our post demodulation. So we have to calibrate this out first. So after calibrate these two DC terms by just simply taking the average mean of it, so we can get one I signal and then the other one's Q signal. So from there, we are able to, since we have one in phase and then one quadrature, so we are able to use arctangent demodulation, which is just take an arctangent of I over Q, so you can get the phase information. So yeah, so if you take an arctangent, it will be like in terms of like this. So it will be 4 pi and then times the displacement divided by its wavelengths, and then plus a small residue phase, which result from the oscillator. So because of the range correlation effect, actually, if in most of the cases of the short range detection, this delta phi, we can neglect its effect. So we can basically use this term and then do the further post-processing. So once we get the time domain IQ and then we do the arctangent demodulation, so later on we just impose some windowing function and then do the fast Fourier transform, so we can get the spectrum domain of the signal that's being detected by the radar sensor module. So from there, we should be able to get, from the chest movement, we should be able to get both heartbeat rate and then breathing rate, which is resulting from the movement of the chest. So you can imagine the heartbeat rate is much more than chest movement. So we impose another digital filter. So first we can obtain the breathing rate, and then later on we impose a Butterworth filter that has a higher frequency cutoff, so that we can see more clearly at the heartbeat rate. And then here shown a measurement setup of two human target, and then they are sitting in front of this metamaterial-based radar sensor. So as you can see, we just set two center frequency. So one is at about 24.3 gigahertz, which will be shooting to target B, sitting in the backward side, and then the other one will just the other one being 26.3 gigahertz, the higher frequency. So that part will goes to the forward side, which is another target. And yeah, so as you can see here, here are the downconverted IQ signal, and then here is the demodulated arctangent signal, which will give you the phase. And then after performing FFT, fast Fourier transform, we can clearly see two peaks corresponding to the breathing rate and then heartbeat rate. And yeah, so here are the tables summarizing these numbers, and we can see they agree reasonably well, which has error less than, I think both of them are less than 10%. So this module, in addition to sensing the human vital sign activities, including heartbeat rate and then breathing rate, we can also use the same module to sense humans' walking distance or their moving activities by mapping because we have the phase information, right, from the arctangent demodulation. So we can map that to the relative distance, so we can get their, we can actually track their movement in this case. So by using the same frequency space mapping characteristic, and then so if we sweep the frequency, center frequency at different frequency, we can basically steer our beam to track human being in different angular location. And we can get their time domain IQ signal separately, and then later on we perform arctangent demodulation, and then we can get the movement of the human being. Yeah, so in this case, this I think this first target, first person, he's standing in the I think it's in the backward side of the radar module. So as you can see, when he's going back and forth toward the radar sensor, right, and we can get his IQ signal, and also we can obtain their relative movement in real time. And also this is another target that is I think is walking toward the broadside of the radar sensor module. So we change the center frequency, and then we perform the same arctangent demodulation and map that phase information to the distance, so we can get the relative movement again for both targets. So we compare the relative movement at these two different frequencies, basically correspond to two different angular location with the ground truth. So the curved target is moving from 0 centimeter to about 60, 70 centimeter-ish. And so compared to ground truth, the displacement error are less than 5% in both cases. So far we have been talking about just one-dimensional tracking. But indeed, if we design this metamaterial-based antenna array in two-dimensional fashion, so actually we can make it into a 2D tracking as well. So the key is that if we make, instead of using one antenna, we use 4 antennas, and then we properly design the antenna feeding network, right? And then we still have this one-port connection. So because of this feeding network, it will provide different phase advance and delay. So if we carefully design the corresponding phase delay and advance, we can actually steer the beam two-dimensionally. So in this case, shown its radiation pattern for this two-dimensional beam steering antenna. So it goes from about 23 to 25 gigahertz. So as you can see here, when you gradually increase the frequency, the beam can actually steer two-dimensionally. So that means we can have more information. Just in addition to azimuth information, we can get elevation as well, right? So so basically, we can use this scheme to obtain more information. So let's say if our two human target, they are in different position. One is sitting and then one is standing. Then their chests are also at different location. So by using this two-dimensional metamaterial type of antenna array, we can steer the beam accurately pointing their chest, so we can obtain stronger information because we have more directive beam that's pointing to the target. So in this case, we have our person 1 that's sitting in a sitting position, and then it's in front of the antenna module, and then person 2 is standing, right? So so in this case, we don't use radar sensor. We just directly connect it to our network analyzer. And so if we let the network analyzers sweep fast enough, so we can still characterize the Doppler signature. So here shown the demodulated, or after taking fast Fourier transform, information for the Doppler signature. So we can still obtain their respiration rate and heartbeat rate for the two people. So one is sitting and then one is standing at different location. Okay, so to conclude, so basically what we have proposed here is to use so-called metamaterial-based antenna structure in both one-dimensional and two-dimensional scheme. So it's just a very simple concept based on frequency space mapping. So by sweeping the center frequency, we can steer the main beam direction of the antenna. So in that case, we don't really need any mechanical motor or rotor, and then also phase shifters to do complex beamforming. And then we don't really need any complex demodulation such as MIMO to do, because that will add some additional computational effort to the baseband architecture. So this is one of our advantage of using metamaterial-based frequency space mapping antenna system. And then from the measure result, we can obtain both the moving distance and then also their vital sign activities at the same time. And as we seen in the beginning, we can make it everything into a portable structure. So we expect that in the future this can be deployed and then to obtain more data in the real world to be used in such like smart health and then smart home and then so on. And finally, just to acknowledge our funding agency. And I'm happy to answer if you have any questions.